Fractals, a new geometry. Let's get deep. An exploration and discovery of the power and profundity of fractals with me, Swami, Math Nerd. We're going to zoom in deep into infinity, into complexity, and along the way discover ourselves again and again at many levels in the realm of the fractal, in all of its beauty in math, in art, in nature, and more. We just zoomed into the famous Mandelbrot set, a fractal of infinite beauty and complexity. Here we see a sequence of the zoom. In the upper left is the full Mandelbrot set, and at the lower right we are zoomed in over 1,000,000,000 times. Fractal. The term was coined by Benoit Mandelbrot in the 1970s to describe geometry that is broken, irregular, and rough. We will discover exactly what this means in future slides. Clouds are not spheres, mountains are not cones, coastlines are not circles, and bark is not smooth, nor does lightning travel in a straight line. Benoit Mandelbrot. This expresses that classical geometry is not an appropriate description for these type things in nature that are rough and irregular, but fractal geometry is. Here's the overview of the presentation. We had a brief introduction, which we will now follow with some history for context, then an intuitive example of fractals branching. This will lead us into some further definitions to understand exactly what a fractal is, then a quick list of types and uses of fractals, finishing with a number of examples, and finally a summary, pulling it all together and giving some takeaways. And here is the nerd poster child himself, Benoit Mandelbrot, with his book that made him famous, The Fractal Geometry of Nature. My first exposure to fractals, and to many people, was the Scientific American article in 1985. It introduces the idea of a fractal and describes how to go about programming them. And so, like any good nerd, I went about programming my own Mandelbrot fractal in Fortran on a Microvax 2 with a flatbed 4-color pen plotter. It was a slow process, but man was it fun. Here are some of my plots from 30 years ago. Now let's get some historical context from this fractal timeline. Perhaps fractals go all the way back to the start of creation, if they're considered to be an underlying governing principle by which the universe evolves. Plato said, God forever geometrizes. Then Euclid came along and pulled everything together in a systematic way. This view dominated for over 2 millennia. There were a few inklings along the way, but it wasn't until the late 1800s and early 1900s that mathematicians started playing with new objects. The establishment considered these things to be pathological monsters, but that didn't stop others. They were intrigued and continued to study them. Here's a visual representation showing some of the people, shapes, and symbols. Fractals are not just mathematical objects, they also occur in nature, particularly in the form of branching, trees, leaves, blood vessels, and more. Let's take a deeper look at fractal branching to get a better understanding. It's all about iteration and recursion, a feedback process where a rule alters an object, then alters the new object, then alters again and again and again. And from this emerges an object of complexity. Let's start with a simple object and rule. Take a line, split it, and scale the new lines down. Now do it again and again a few times more. The result is an idealized, symmetrical proto-tree of sorts. Apply different rules to get different trees. Next, Take it into the third dimension. Finally, add some lighting and texture to get realistic looking trees. And if you're artsy minded, you might even make this tree. Now for some terminology to get at some properties of fractals and gain a deeper understanding. Simplexity. This means that from a simple basis, a complex thing can result. This is somewhat profound in that one might think a complex thing must have a complex origin. Fractals are self-similar. That is, they exhibit self-similarity. This means they have the same appearance at different scales. The whole is reflected in smaller and smaller parts. Most intuitively, this is recognized in the spatial dimension of distance, but it may also occur in time and other aspects. Fractals also follow a power law of scaling. This can be summed up as an ever larger number of ever smaller pieces. This can be seen in the tree example previously covered. There are many types of fractals. Some are mathematically precise, while others are statistical. And within these realms, they can be chaotic and random. The Mandelbrot set is an example of a complex polynomial function fractal. The trees, an L system. And later, we'll talk about electric sheep. And there are many uses for fractals in the creative realms of art, music, animation, and whatnot, as well as applied areas. Dynamic systems, biology, forestry, astronomy, even in economics and the stock market, where Mandelbrot particularly had an interest. And finally, some examples from computer animation to DNA, time series analysis, and art. Fractals were used to great effect in Star Trek II, The Wrath of Khan.
He created a whole new planet for Star Trek II, The Wrath of Khan. It was the first ever completely computer-generated sequence in a feature film.
Fascinating.
Made possible by the new mathematics of fractal geometry.
Here, the fractal mountain is generated much like the tree. The simple object is a triangle, and the rule is to divide it and pull it up. Do this again and again, and throw some randomness in there, and voila, mountain. For realism, add lighting and texture. Next, we come to Dr. Pelionis and his intriguing ideas on the genome, specifically to the recursive genome function. Note recursive, giving us a hint of fractals. In his thinking, he addresses two problems in the genome and DNA, specifically the so-called junk DNA, as well as the central dogma of molecular biology. We know the full sequence of DNA, the genome, but we don't understand what most of it does. Some have labeled it junk. But is it really? The central dogma concerns the flow of information of the DNA sequence. It says it can go from DNA to RNA, from RNA to protein. It can even go from RNA back to DNA, or from DNA to itself, or RNA to itself, but it can never go from protein back to RNA or DNA. Let's make some sense of this busy graphic. Iterative access to regulatory DNA. Basically, it shows two types of DNA, one for encoding protein and one for regulating. In this scheme, the protein encoding DNA creates the fractal template. This then sends information back, violating the dogma, to the regulatory DNA, which creates the next iteration. This goes back and forth until it runs out of regulatory DNA. Dr. Pelionis and his team have spent many years developing these ideas and has now put them into practice through his company, Halgentech, and a program called FRACTOGene for analyzing the DNA genome. The aim is to detect variation in the fractal characteristics of the genome and also possibly of the tissues generated, thus providing a valuable medical diagnostic tool. It should be noted that these ideas are not mainstream and still need to be borne out. Moving on to time series analysis. Here we have an EKG of the heartbeat. Most think it's regular, but in fact, there is a fractal noise nature to it. This is observed on the scale of time, and the self-similarity is in the degree of statistical randomness. Other time-varying signals exhibiting fractal nature are brain waves as well as seismic waves. Some claim even the stock market. And last but not least, on to fractal art. We will look at UltraFractal and electric sheep. UltraFractal is like Photoshop for fractals. You have layers and mix modes, gradients, and more. Here's a gallery of awesome artwork created by using UltraFractal. Here, enjoy some more. So, do androids dream of electric sheep? This question was posed by Philip K. Dick in his book of the same title. It was then taken up by Steve Draves in an amazing interactive screensaver. He envisioned the sheep to be digital life forms that could breed and evolve. Multiple fractals are combined, and parameters change over time. Users vote up and vote down, allowing some to go on to create other generations. Here are several sheep accompanied by fractal music generated by a chaotic dynamic system. Okay, that was a lot to chew on, so let's sum it up, tie it together, and get our takeaways. So, fractals are a new way of looking at and describing things. That is, things that are rough and irregular, unlike the classical geometry. It's about process, that is, growing a thing. We make things, we build things, but nature grows things. And it does this through iteration and recursion, a kind of feedback process. And in this process emerges self-similarity in space, time, and other. Also, infinite complexity arises, but it comes from a simple basis, hence simplexity. And the concept of fractals is very fundamental, therefore it spans a wide range of disciplines. And of course, if nothing else, fractals are cool. So there you have it, fractals, a new geometry. Thanks for your time, attention, and interest. To learn more about fractals and other cool mathy stuff, check out my group, The Winged Circle, at the address on the screen. Surprise! Bonus slides! Here are some slides I had prepared in anticipation of possible questions. So, let's get started. The first topic is the making of the Mandelbrot set, followed by fractal dimension, and finally, the connection between fractals and chaos. The making of the Mandelbrot set. It looks a bit confusing and complicated, but it's not so bad once you get the idea. In fact, just a middle school or high school level understanding of math and programming should be enough. Actually, I think I can get the gist across to anybody who's willing to put in just a little bit of effort. The Mandelbrot fractal is actually a collection of points, a set, that live in a special two-part number plane. You can just think about it as east-west and north-south. Each point on the map gets tested. Some make it in and some don't. The ones that make it in are black. The ones that don't get colored based on a special property. Here's how it works. The equation at left says z goes to z squared plus c. That funny looking equal signs means it's a recursion equation. So the answer is fed back in, and then a new answer is gotten, and a new answer, and a whole sequence of numbers get generated. Let's test a point. The yellow point, labeled C by the word spiral. It generates a sequence of numbers called an orbit. You can see that sequence generated to the left under example. First, we let the z equal 0. This is called the orbit of 0. Plugging z in gives us a value. We take that, the red one, and plug it back in. Using again the same yellow value of c, we get a new number. We plug that back in, and we keep doing this over and over and over. Some orbits spiral in, like this one. Others, like the green one, cycle around and around. They are in the Mandelbrot set. They are said to be bounded. Some orbits, like the blue one labeled escape, fly off to infinity. Different points take a different number of times to get there. That's called the escape time, and the colors show how quickly they escape. That's it. That's all there is to it. And now you know. Okay, for the mathematically inclined, you may have noticed that I used non-standard terminology. I do this to get at the essence of the thing and not to get confused in certain language that can be misleading. For those who want to know, the two-part number plane is the complex number plane, and the two-part number is made up of a real and imaginary part, though neither is more real or less real than the other, and it's not complex complicated. It's like an apartment complex made up of parts, two parts in this case. The imaginary number is represented by the letter I, and it means the square root of -1. Although this is an unusual thing, it behaves much like other numbers in the arithmetic. Lastly, the equation is a relatively simple quadratic equation, a complex quadratic equation. In fact, this has an unusual property that when you multiply numbers, you get a rotation in the complex plane. So this equation represents a translation as plus c and then a rotation as z squared. This can be seen in certain fractals like this one where you get lots of spirals. On to fractal dimension. This is one of the more perplexing things. Though a fractal does not have to have a fractional dimension, many of them do. Here's a nice table showing a collection of fractals and their respective dimension. Notice that the Mandelbrot set has a dimension of 2, an integer. Most of them are fractional though, even the ones that don't show a number there. We'll explore that further. Surprise! There's more than one kind of dimension. Topological dimension, or the traditional sense, meaning the number of independent directions required to locate a point in a space. This is the one you probably learned in school. But there's also a fractal dimension, or the Hausdorff dimension. This is a modern view, and it considers the scaling behavior of an object. And recall that the power law of scaling was a special property of fractals. As it turns out, the fractal dimension is always greater than the topological dimension. Let's get a feel for this. Consider a straight line. If you divide it by 2, you get 2 identical segments. Divide it by 3, you get 3. So how many new pieces are there as the object is divided? Or what is the relation between scaling and number of pieces? The relation is the number of pieces equals the scaling factor raised to the dimension. Since d is in the exponent, we can use the logarithm to pull it out and get d equals to the log of the number of pieces divided by the log of the scaling factor. As an example, consider the Sierpinski triangle. This fractal is created by starting with an equilateral triangle and popping out the center. Then with the new triangles, pop out their centers. Do this again and again. If we look at the diagram here, we can see that if we divide each side in half, we get 3 pieces. Divide by 4, we get 9. By 8, we get 27, and so on. Plug this into our equation, and we get a fractal dimension of 1.58. So, what the heck does that even mean? Well, there are 2 ways to look at it. One, it's the degree to which the fractal is space-filling, and 2, it's the degree of complexity of the fractal, how irregular and rough it is. To get a better understanding, let's look at the Hilbert curve and cube. The curve is space-filling. In fact, it can touch every point in the plane if taken to the limit of infinity. Therefore, the line is 2-dimensional. Likewise, the cube fills all of the 3D space. Therefore, this line is 3-dimensional. This arrangement has an interesting property. Even though it's a line, and you would have to follow that a long way to get somewhere, by its nature, its fractal nature, you can access a location quickly, as illustrated by the Hilbert cube and the laser light pointing to the center of that line. To tie things together, here's a nice graphic that summarizes things. On the left, we see the traditional line, plane, and cube. Successively it gets divided, and we can see how the number of pieces grows and how the respective dimensions are calculated. We get the traditional 1D, 2D, and 3D for the shapes. On the right, we see a nice representation with the Euclidean shapes on the left. The point has a 0 dimension, a 0 topological dimension. The line is 1, the plane is 2, the cube is 3. But in between those places, where the fractional dimensions live, we have the fractal dust, the fractal curve, and the fractal surface. And last, but far from least, and an aspect that catches the imagination of many people, is the connection between fractals and chaos. Represented in the Venn diagram, we can see an overlap between fractals and dynamic systems. Dynamic systems may become chaotic and may exhibit fractal nature. Chaos is unpredictable, yet it can result from a fully determined description. It's important to note that these systems are connected in a nonlinear way. The result is that a relatively simple description can manifest quite complicated, even chaotic behavior. The first example is bifurcation, that is, successively splitting in 2. It comes from the logistic map, a quadratic recurrence relation that models population growth. Notice the x times x gives an x squared term, so it may come as no surprise that this is actually related to the Mandelbrot set. The sequence of numbers divides smoothly until at one point it starts to oscillate between 2 values, then 4 values, then 8 values, but at some point it starts to unpredictably and chaotically bounce between values. From this point on, there are infrequent stretches of order, but for the most part, it behaves chaotically. The second example is the Lorentz-Strange attractor, a simplified weather model. It is famous for generating the famous butterfly effect. In effect, even a small change to the system, such as the flapping of the wings of the butterfly, can lead to wildly different outcomes, even chaotic ones. And for the technically minded, this model is a system of coupled nonlinear differential equations, and the plot shown below is in phase space, not in physical distance type space. The phase simply represents the state of the system at a given time. Lastly, for a great layman's introduction to chaos in fractals, I highly recommend the quintessential Chaos: Making a New Science by James Glick.